My name is Adrian Lucas and I am in charge of the stress analysis.
My name is Noor Saleh and I'm in charge of the force analysis.
My name is Eric Rosenfeld and I'm in charge of the geometric design.
My name is Seth Hutchinson and I'm in charge of the kinematic analysis.
This is our ME-154 mechanical engineering design project for San Jose State University, spring 2018.
The robotic arm was designed to grab and pick up items that are too dangerous for human interaction. The arm's design specifications were to have a maximum reach of 2 feet with a full 360-degree rotation that could lift an object that weighed around 10 pounds. The robot arm calculations and analysis were conducted on a smaller scale due to prototyping purposes and manufacturing constraints.
The arm was designed using the graphical method based on the desired locations for when the arm was retracted and when it was fully extended. There were 2 sets of 4-bar mechanisms that were directly connected. The coupler for the first 4-bar was also the ground link for the second 4-bar. This was done because it allowed the arm to have more maneuverability while still retaining its reach. The 4-bars were also designed so that the theta 3 angle would not experience drastic rotation even as the link attached to the motor went through its full range of movement. This was done because we did not want the claw, which was attached to the second 4-bar coupler, to over-rotate and make it difficult on the wrist servo. The robotic arm consisted of 4 4-bar linkages at the base, giving our claw freedom in the XY plane. All of the linkages were 3D printed with PLA material, and a wooden block was used for the base. The coupler of the second 4-bar linkage was attached to another servo that adjusted the claw to the horizontal position, allowing for pitch in our mechanism. A stepper was attached to the base of our mechanism, allowing for yaw. The claw itself was another 4-bar mechanism controlled by a servo and 2 gears, allowing for movement in the Z-plane. The base links attached to the motors were designed with a teardrop shape and an extruded flange to withstand the torque of the motor. Sleeves were designed for our motors with a T-shaped head to be press-fed into each motor-controlled linkage.
In order for our robotic arm to carry the required load at the end of the claw, our linkages had to be at full extension. Due to the moment at the base, links 1 and 2 would experience the most shear bending force at that connection. The mass moment of inertia was calculated with the object's mass balanced along the x-axis by using SolidWorks. Due to the high torque required to turn these links at the base, the motor had to be accompanied by a gear drive. The sum of forces and sum of moments was applied to each link. In order to solve for these force equations, a 28 by 28 matrix had to be solved. The forces were confirmed correct by summing up the forces to equal 0 at each link.
For the stress analysis, the arm was analyzed looking for the maximum load that can be applied. We assumed the yield strength to only be 1/3 of PLA's actual yield strength to account for manufacturing errors. Accounting for various failure modes, bearing stress resulted in the smallest force that could be allowed. Assuming a safety factor of 3, the max load that could be applied would be 3.587 newtons. This calculation assumed that the max load that could be applied directly transfers only to link 1 on only one side of the mechanism.